Today, I'll talk, there are a few little items on aluminum alloys that I'd like to go back on, and then we'll spend most of the lecture talking about plastics. I brought 3 examples, 2 of which are broken pieces, and the other one is just a very complex design. This is a filler neck that is put on a jet ski. So they drill a hole in the hull, put it in, and they just have a set nut from the underneath to hold it in place with seals and everything. It's a very cost-efficient way to make a part like this because you just mold it. There's no need for machining or forging threads. The threads, everything is all part of the mold. One disadvantage is it's more intended for relatively large quantity. You need to spend some time making a good mold that have the proper cooling, the proper supply of material to make it happen. And you can see on it the mold lines, and it's not a complex, but it's an interesting part that was made in large volume. So the aspect that I didn't emphasize too much about the aluminum, I remember mentioning the overage, underage condition as far as corrosion, and I just said for mechanical properties it's the opposite. So this is a plot that shows how for a given yield strength, when you have an underage condition, so it's we have 2 alloy series here. So if we look at the dashed lines in this direction, we're in that range, that bracket. If we're overage, we're at the bottom of the bracket. If we are underage, we're at the top of the bracket. So we're looking at about 25–30% increase in fracture toughness by being underage. And the best way for you to hopefully remember this is what brings fracture toughness. So if I have a crack and I have some plasticity at the tip, and I have another crack, we all have the same yield strength, but because of strain hardening, I distribute my plasticity to a bigger area. It's going to absorb more energy. It's not because of a difference in yield strength. In both cases, the value of the stress here, I'm going to put it sigma yield, is reached locally at the surface. Both cases. One difference is here, it hardens, and therefore it becomes more of an elastic, and it keeps pushing the plastic deformation away from the center of the plastic zone. And therefore you get more strain hardening, and you get higher stress values inside that zone here when you have more hardening. Why the underage alloys have more hardening? It's just the way we straighten them with these very fine precipitates. The precipitates, when you deform, just become they remain continuously useful at increasing the resistance to the movement of dislocations. When you have very large precipitates, essentially the dislocations start going around them, and therefore they're only helpful up to a certain dislocation density, and after that it just goes around through the interface. To maximize the strength of these little precipitate in aluminum alloy, they need to be still part of the material as opposed to being an inclusion that you can go around because there's no cohesion of the interface. That's the difference I'd like you to keep in mind. I mentioned about an isotropy, that you will have different properties in the plane where the material was rolled. So if I have a sheet like this that's big and relatively thin, if I start with inclusions that were round, they become more or less like little pellets. Maybe they'll have they've broken down into pieces, but you'll have a lot of imperfections that are planar in the same plane as the plate. And therefore, if you have a crack that is going this way, trying to separate and open it up, it's a lower resistance. And that's what those plots show here for the ST direction. You have about 30% less fracture toughness. The first column for each of these four alloys is the iron and silicon content. It gives you an idea on how many inclusions you have. So you can see for these two alloys have the same chemistry except the amount of inclusion, and there's a small increase in fracture toughness as a result. But when you get to the 7000 series alloy, the one that's higher strength in general, you can see not that you double, but you increase by more than 60% your fracture toughness just by having fewer inclusions. And that's related to flattening them, essentially putting them a way to get the material to do all that plasticity that we were talking about earlier. So as soon as you put on these big inclusions, they are an easy way to generate voids or grow through the interface, and therefore it reduces the fracture toughness.
So those inclusions are non-coherent in the matrix?
Yes, that's right. Most inclusions are. The only way you get cohesion is when you remain very small. And that's what we do in the aluminum alloys when we control precipitation. Thank you. Last thing about aluminum alloy, I mentioned that it is sensitive to stress corrosion cracking. This plot is intended to show for the 7000 series how different the stress corrosion cracking is between a peak aging, so highest yield strength, and an overage situation. These are fairly similar alloy. These are all overage. It's a T7 as opposed to a T6. What you're looking at for the vertical is the stress corrosion crack velocity. So we have a change by 5 orders of magnitude on how fast the stress corrosion crack is going to grow. It's more or less saying that for stress corrosion cracking, even if the precipitates are very fine, they reduce the resistance to cracking in this case, because you have time and you have the environment to create the decohesion. And there's an inverse relationship. If I say I want to put 4% of inclusions in the material, if the pieces are big, they're going to be separated apart. If I take that 4% and now make it nanometer size particles, now they're very close to each other, so they can interact more easily and help the crack to grow in the presence of hydrogen and chloride and acidity. So that's what happens in aluminum alloy. Because we're switching to plastics, I decided I was going to talk to you a little bit more about those high strength steel material that we talked about. The reason is we talked about increasing the fracture toughness and making them really good. You can have very high yield and very high fracture toughness. This is the upper curve right here. So even if you're increasing the yield strength from say 1000 megapascal to 1600, your fracture toughness is still pretty decent. And that was the retain austenite that we talked about just a little bit. Now, if you are looking at environmental cracking, it's a very different effect. So environment cracking is this lower curve here. You can see, about a 5-fold decrease in the resistance to a crack that's existing if you have the environment, if you have chlorides, temperature, hydrogen over time that is locally at the crack tip. And that's how a lot of pressure vessel applications end up being decided. They'll decide, oh, we want a good purity alloy. We don't really want to go crazy with strength because we know we're going to have all these other problems if we do. So if you're taking, even if you're taking at a high pressure application, in a lot of times you'll be willing to put more metal to reduce the stress level and avoid those types of issue. It's something that has been a challenge for oil pipelines, developing steel alloys for oil pipeline to make sure that they don't stress corrode. If you have the whole installation in place, they set up some minimum useful life, and they don't want to have to go and replace everything, because if it does happen, it's going to happen at a lot of places. That's the unfortunate part of the stress corrosion cracking. It's not only at the location that you have a super high stress, you need some stress, and you need the environment. And then it's mostly a question of time. Going back to the steel for landing gears, there are quite a few interesting aspects to it. Is a landing gear gets fully loaded for maybe 5 seconds per flight, and it's only in landing. So you're not when we're talking about slow cracking by stress corrosion here, it's not the same thing than if you're looking at a pressure vessel under vibration. So this specific consideration of resisting stress corrosion cracking, and plus there's more control over the condition, they can put a protective coating and control the condition of that protective coating, have inspections. So they are willing to deal with that risk, but in other industrial applications you wouldn't. And that can help. It's not only costs that make maraging steel a little specific to aerospace and high demand application. It's all the other consequences that come with it, like this stress cracking. All right, so plastics is something that I've learned when I was doing my master's degree thesis. It wasn't taught as part of my metallurgy underground program, but it's become, obviously more popular since then, and it's probably something that you know as much about as you do about metals. We'll try to go through a few examples of things to think about when you're selecting these materials. So Professor Eager already mentioned it's used a lot for underground pipes because you don't have to worry about corrosion both internally and externally if you can maintain your stress level very low, and we're going to cover that today. So I'm showing all sorts of pipes and fittings, and I have a pipe here that's for fire sprinkler. I brought this to the other fatigue and fracture class yesterday, and somebody thought it was for gardening sprinklers. So it's intended to go up to about 200 psi, and it failed through slow cracking from the inside, and we're going to talk about that later. I have a molded component. This is a single piece here that goes as a shield under the hood, made out of essentially a nylon alloy. Comes with all the piping, and the cap's probably a separate part, but other than that, it's a very cheap way to make a complex part. It does have a high compliance, but it has good ductility. So if you don't have a lot of load, in general, if you can keep your stress level low, you can use these thermoplastics for sustained load application. A lot of other times we use them thinking like those chairs. I bet you if I put the maximum load, sitting load on it for a week, it probably just fail on me. But they decided it's not going to happen. Yes?
So this failed under cyclic loading or creep or what?
Just pressure, internal pressure.
It was just too much for the structure of the pipe?
It's because the resin degraded, and we'll cover that. But it was a constant load, and there were multiple cracks initiating slowly from the inside and growing outside. Very similar to a stress corrosion cracking of metals. Good question. One thing to think about dealing with, most plastics at ambient temperature will creep. Creep is a process of deforming just under a constant load. So if I take a piece of metal and I put load on it at ambient temperature, most alloys, except lead and a few ones that are very low melting point, will maintain the load. They will act like springs. Plastics just in general don't count on it. There are a few high temperature plastics that have very limited creep. And then you have the polyethylene that would actually just go everywhere you want to go with it because it's so flexible and it's above its glass transition temperature. And we'll talk about that later. I don't want you to get all worried. So we take a generic plastic, we put it under load, and what that slide shows you is on a log-log plot, a lot of times it's linear, except if you go into that failure mode. So the green curves on top is where eventually you reach a condition where you're forming a crack, voids, defects in your structure. If you are not going that, so starting with the red lines here or below the lower red line, you can essentially reduce the amount of stress, of additional strain that you get over time. I mean, it's never going to become completely stable, but the amount of stretching will decrease over time if it's under constant load and it's not going to a fracture. And that's what we use for polyethylene pipes underground. We know at the beginning they all sag, change their shape, become a little bit oval, but then eventually it's all going to become more or less static. How did that happen? The macromolecule stuff is not something I want you to worry too much about, but it's good for you to keep an idea about why a polymer does things a different way than another one. So it's made out of these very long chains. The base of the chain is a carbon-carbon bond, and then you have all sorts of other bonds next to it, and I have a schematic of that later. But the idea is if I just take a bunch of these C-shape here, if all I'm asking is for these two guys to rotate a little bit, not a big deal. It can happen as part of the elastic deformation. If I'm asking, say there's another one chain, and I'm just going to draw it as segments now, that's going over it, and now I say, well, you know, I really want to have some shear, so I'd like this chain to go over that C bond here. Well, now that requires energy or time, and that's where viscoelasticity comes in. So if you're going to move over a certain distance relative to the other molecules, that's what we call viscoelasticity.
How does time actually help that happen?
Okay.
Because in mechanical engineering, we go, it's like very cursory, like, oh, they're all tangled up, and then they kind of untangle over time. Why would they?
The question was, how does time matters? One aspect with polymers that, you know, I answer your question two ways, so I try to answer it from a mechanical standpoint. If you vary the temperature on the mechanical testing for a specific type of plastic, you can see the exact same response as you get by changing the rate, the frequency of running, you know, a cyclic experiment. So that's just a confirmation that we're not, you know, talking out of the blue, that the phenomena is happening. Why the phenomena is happening is all related to thermal activation. Thermal activation means this chain is moving. So we had these R2 chains going here. Not sure which this is part of this one. This chain is moving some. This chain is moving some. Just out of randomness, they may switch on you without requiring any load, just because of vibration between them. So if you have just a little force, whenever that random jump happens, it will happen and not come back. And that's where you get your strain just by applying a little force. If you want it to happen now, That's where you can't wait for that random fluctuation to hit that area that you wanted, the switch you want to make. So now you need to apply more force. So when it's half trying, it's still jumping over. That's, I think, the best way to think about it. It's obviously the more you can eventually really move these molecules with respect to the other, but you have to reach a higher stress level than what happens in viscoelasticity. Viscoelasticity, essentially, you're there, you're sort of pulling, but you're hoping for some help from the vibration. That's the best way to think about it. So the more you're patient, the more you'll get out of it. So I have these, this is from a book on viscoelasticity that was actually very interesting, where viscoelasticity that we will talk about like minutes maybe at ambient temperature is essentially going from A, B, and C, where yes, I made those changes happen. I moved a little bit in this direction, so I have to twist to go around the other guy, but if released, what's most likely to happen is I'll come right back because I did stretch my chains. These chains of macromolecules just like to be fully random. Fully random means they're not all stretched. They have a certain amount of proximity between the ends. There's a statistics to know approximately if you have something that is 10 meters long, it may just be confined within 1 meter. Just because when you try to make turns left and right, you don't go as far as if you try to go in a specific direction. So what happens in D is what some people will call viscoplasticity or permanent creep, where now when we had our two chains here, this one and this one, now we can actually take this one and move it further. And that is becoming very complex to think of, because if you reheat the plastic, I've seen experimental results where what we consider a permanent viscoelasticity will actually reverse on you. So there's a fine line. There's always going to be some history in the material, and the distinction between C and D, to me, yeah, maybe, but it's very limited. It's more limited than people think. For practical use, obviously, it's nice to think that eventually, when we get into this mode, this is more or less of a viscous mode, where the macromolecule move with respect to each other, and sometimes your creep rate becomes constant. And I've seen that in my own experiments. It's useful to know, because then your life prediction is changing based on that. Another thing for you to be aware, a lot of thermoplastics that we talked about are not just random chains everywhere. They do have little crystals in them that we call crystallites. Polycarbonate is an example. It's transparent, so it's fully disorganized, fully amorphous. But polyethylene, PVC, ABS, the majority of the plastics have what we call spherulites. So what happens is it's originally completely disorganized in a melt. And then when you start nucleating crystals, they grow from the center of this outward until they meet other spherulites or grains, or you can call it what they want. One of the main difference between these spherulites and grains in metals is it's a combination of very small crystal that we call crystallites and amorphous zones, because you can't organize and fold in a perfect crystal these macromolecules. You'll have knots, you'll have parts of the macromolecules that don't fit, and that's why it's organized in a little lamellar function like you have here. So you have a crystal, it's called a crystallite. In between you have essentially an amorphous polymer. Now obviously you can think that the way you cool down, the way this part here, this is made in this way, it has these ferrolites in it. The way you cool down from the melt in the mold will affect how this will look like. If you cool really fast, you get to a temperature where you can form a lot of these ferrolites, but they don't have an easy time to grow. So you have a bunch of small ones. If you're at high temperature, if you get one to go, it will grow more easily because of the kinetic. It's got more thermal energy to do the organization. The reason why when we take a piece of plastic in the lab, say we start with a duck bone like this, and we can end up with something that essentially looks like this. So we're talking about 300% elongation. Is you break down that spherulite when you start the deformation, and it becomes more of a fibrillar structure. And that's what nylon cords are made out of. You start producing the nylon as a melt a little bit like this part is, and then you stretch it to organize more, orient more the macromolecules and the crystals. It's something that happens also in making that pipe, and that's why you get very different properties than if you start with that, I'll call it a solidification structure, but it's whatever, or nucleated and crystallized, semi-crystallized structure. The semi-crystallized structure is going to deform under a lower load, and at the beginning it doesn't have, it has hardening, but it doesn't have that much hardening. That's why you get into forming a neck very quickly. But when you're down the road here with a nylon wire or a nylon rope or anything like that, it's so stretched, and it's fairly resistant to very small imperfections, but it is notch sensitive, and we can go through that as a disadvantage for a design later. I'm going a little fast. Any questions? Anything? Yes?
So when we learn injection molding, we're taught, the flow of the plastic is very important to how the part performs mechanically.
Yes.
So is that kind of the idea when you're forming? I remember from quals, there's like when you inject into the molds, you can form those. You're basically lining up the polymer chain.
We'll draw that. It's different a little bit. This is more like a drawing process, an extrusion process. If your goal is to mold a product, what you want to do, in the case of the blue part here, is say I have my wall going this way, and then I have some extra material here. The worst thing that could happen, what I would rather have, if this is going to be a high stress region, is have the flow going through it, because that creates a little bit of a boundary layer. It helps the characteristics of my skin. I just want to have as much flow out there as I want to. But if this is the center line of the part, you get the opposite effect, because when you start completely filling this in, you're going this way, you get it this way, and then you do the same the other way. This is a mold line. This is going to have very low strength. And you want to design it so it's outside your high stress region. There was an example piece that Professor Eager brought to the class where essentially have two pipes butting each other, pushing it enough to extrude enough material. So what happened is, I'll do it in the cut view, and we're only going to do half of it. So we have the two parts here. They get into contact, do two halves looking in a cross section. You try to make sure you have enough deformation and you get the half of it to share and merge together, and hopefully you get some going the other way, so that you have as much mixing of the two of them. So mixing the macromolecule at a joint line, mold line, is very important, and this called the skin effect is helping you in injection molding. But you have to think about, like, if I also have flow going this way, who knows, is it going to fill this in and then move up? That's not going to give us as much orientation in the area that we're interested. So maybe we want to make the gravity to our advantage. So it's a good comment. It's something that happens. This happens too. We try to avoid it. Crazing is essentially the formation of voids in the thermoplastic. It will happen typically below the glass transition temperature or near. So polyethylene doesn't tend to craze too much at ambient temperature because it will flow and deform without the formation of these voids. So the reason why you form the voids on the first place is you try to deform as an overload. It can happen when we were talking about our spherulites, and I have an image here. These are more or less spherulites that you can see on a cut section, a little hexagonal equivalent shape. So you're trying to stretch these spherulites, but right on the nuclear, you have a lot of triaxiality, you have a lot of tension, and you can start forming voids. Now, it will be different than in the middle because you start forming voids. That happens, but those macromolecules still don't want to separate around it. So you form these fibrils that you see right here, and some people call it stress whitening. So if you take a piece of plastics that's relatively rigid, you can see that happening. I was able to see it, I remember, with dry nylon, because it's at the temperature lower than the last transition temperature is above ambient. So it was in a relatively brittle stage. So you can have in those fibril a lot of strain hardening. They are very oriented, much more than those nylon cords that we're talking about. So they help forming a bridge. A craze is not something that is exactly like a crack because it can resist some load. Now, if you put a cyclic load on it, then you eventually buckle and collapse the whole structure. So it is not necessarily something that you want to have all the time, but it's not uncommon either. And if you play with some material parameter, like if you increase the molecular weight, you can make those crazes more stable and essentially improve your material properties. So I said it depends on the temperature and all that. So you have it here between having a crazing, that's the lower half of the curve, or having more of a shear type process. So we're all talking about a temperature below the glass transition temperature, and it varies for different materials. So polystyrene, it used to be the little clip to hold the bread paper, the bread bags were made of polystyrene. So you can see that it will form these crays, not almost no matter what, but it will. So will polypropylene. This is nylon polycarbonate, and the PEEK, which is a very high temperature material. So polyethylene is on the other side, and polypropylene can be on the other side depending on your loading rate again. So this is not, an absolute theory. It depends on how fast you're deforming. I wanted to talk a little bit about the effect of material parameters because it led to me disagreeing with engineers before. Not that I like or dislike that, it just happens. People think they're going to go run a tensile test. They get a higher strength. They're happy, right? What's wrong with this theory? They get a higher stiffness. They get something that, you know, they can say, oh, you know, we really made it. We really made it happen. Well, if I look at it here, this may or may not be the best example, but I can take this point on the strength curve, and I have a strength that's about 12.5 KSI, and then I keep going here, and I have a strength that's maybe 15% less. Well, somebody may say, well, I like the 15% more. That's my test. That's what I'm choosing. But we're looking here at a difference in molecular weight of about 60%. All of that will show up in creep, not in the tensile test. So if I essentially decrease the molecular weight, so that's going from this point here, the low point, to a higher value, I get a better modulus, and I get a better short-term strength because of how these crystallites form. I can form my crystallites more nicely. I can have more percent crystal because it's easier to put them all together. If I go to creep, I guarantee you it will be the complete opposite. The shorter molecules will be flowing more easily through the network than the longer one. And the 40% difference in molecular weight is very significant. So that argument came about before, and I eventually had to run the test and prove we had about a factor of 2 in the creep strength, you know, for a fixed number of hours. We couldn't go very far. We only did it like 100 hours or something, and we had a factor of 2 at 100 hours between the two resins. Yes?
Is there a way to accelerate a creep test?
Yeah, you put more weight into it. You have to be careful about what you're looking at, because when you accelerate a test, you can get a failure mechanism that's different. So it's okay to accelerate viscoelasticity, because viscoelasticity is moving things around. And the best way to do it is actually to increase the temperature as far as a test. But what happens when you do that, you don't get the same risk of forming crazes, for example, because that's temperature dependent. So it only helps you predict better the viscoelasticity response. And that's my personal view of what people do. Is most of the time that's what they do. They manage to accelerate it a lot by going into a higher temperature. If you wanted to simulate a creep failure, arguably you can do it by fatigue, because you really get, with the cyclic stress coming in and out, you just get more fluctuation. You do get an equivalent, a lot more creep deformation to happen under the same maximum load. It's a little bit hard to relate, you know, in terms of scaling the time as opposed to the cycles, but in terms of the process, there are a lot of people that have shown even a similar fracture surface by going under constant load and cyclic load for creep of polyethylene. Yeah, effective molecular weight. So we talked about it. These are not that big. I mean, we're going from an order of magnitude in molecular weight, and we have a threefold change in our fatigue life. So the effect of that molecular weight, I can't emphasize it more. If you only remember one thing about thermoplastic, just think of that. This is just something for your benefit. The polyethylene is a very common greenish pipe we use for underground. Polyvinyl chlorides, so that's PVC. I didn't bring one, but it's also very common. It's either white or grayish. And then you keep going down the road. When you get to polystyrene, it looks almost the same. except this is a benzene group. So it's so much bigger on the side of the polymer chain, and that's why you can't have these movements of one chain to the other and starts forming craze as soon as you start deforming it. So it's very susceptible to increasing the volume. I talked about glass transition temperature. So the idea I'll tell you the fundamental definition. Fundamental definition, you'd look at the volume against the temperature. And what you see with most of these polymers is they have a transition here. So above a certain point, there's just a lot of air in the polymer. And it gets to a point where the air is becoming more minimal, and it's essentially air that you absolutely need to keep the distance between the bonds. So it's a little bit the same way of thinking at high temperature. Maybe I have more oxygen. I can have more oxygen or permeation of different salt in water at high temperature that I'm going to have when I cool it down and freeze it. So this essentially is our TG, and typically people don't run this experiment to calculate it, but the bottom line I want you to keep is if you take a material like we talked about polystyrene has a high TG, but if you test polystyrene at its TG with polyethylene at its TG, they'll behave a lot more in a similar way, and it still have some differences, but in terms of viscoelasticity, they'll be a lot more similar. So when you're dealing with like PEEK is one of those materials that has a very high glass transition temperature. Teflon has a high glass transition temperature, and it just affects how you think of it at the end in terms of how it will deform. This is just a curve for the time temperature equivalence. One curve is at a fixed temperature. That's to the right. And then we have a test looking at different temperature. And you can just put the curves right next on top of each other. And that's all related to the viscoelasticity, the time dependence to move the chains one around each other. I mentioned the tensile properties. You shouldn't think of that as being very important for your application. It's a little bit like this. You've seen it too, but you haven't seen it. It's just a piece of a binder that broke after about, it's my old downhill skis, the bindings for it. It failed after about 15 years. It's an environmental effect, although you can't rule out creep because it's the cap holding a spring. So even if it was, actually it's probably, in terms of creep, it's when it was in my closet that it was being loaded and deforming more at the higher temperature than when I was outside. The outside was just bringing more of the brittleness of the behavior that came also because I ran out of antioxidant with this thing. When you start losing the coloration on these types of plastic, it means your antioxidant package is going away. And now your chains are becoming shorter. It's a more brittle behavior. It will also creep more. As far as notch resistance and impact resistance, what I'd like you to think about is it's very much molecular weight dependent. Because if I make a notch or an impact, I need to spread into that whole network of macromolecule. And the longer the chains are, you can't break the chains very easily. So they'll try to move one way or the other. The bigger they are, the harder it is to separate them. And that's why all the fracture type of property go up with molecular weight. On the other hand, the short-term properties, because of the crystallite, it's harder to form that very tight crystallite when you have long macromolecule. They all go all over the place. So I want to go over environmental resistance. That's a PVC pipe that failed at the position of the solvent cement line. So we have a crack initiation here, a crack initiation there. We're looking at cracking of the fitting that's over the elbow. That happened over time. It was very slow cracking at the beginning, and then it progressed. There was definitely degradation of the resin by the solvent. And it's not atypical, like gasoline tanks are very well known to become softer and also more brittle because of exposure to all the solvents in the gasoline. This is our fire sprinkler pipe. So it started on the inside. There was probably some contamination with oil by the plumber who put this system together, and just a little bit of oil with those resins under pressure, CPVC, chlorinated PVC. It has a higher glass transition temperature, so it's not going to grow as much over time in service at ambient and elevated temperature. Essentially, call it environmental cracking, but it's initiated by a degradation of the resin on the surface. And it didn't take much time to start the cracks because we have so many. If these cracks, if we're looking at one big crack growing, it'll be a different answer. I'll be talking differently to you about it. This is another system where it was forming blisters on the outside. It's a system that had PEX on the inside, so it's a cross-linked polyethylene layer, so it's more creep resistant because you cross-link it to some extent. It's not like epoxy, but it has some permanent connection between the chains. There was a layer of aluminum to act as an oxygen barrier, but also to help with bending the tube and keeping its shape. And then we have the outer layer. So what happened is they put potable water in it. Initially, the idea was to use it for radiant heat. That's how it was put together. That's why you want to put the oxygen barrier so you don't contaminate your furnace with oxygen all the time. And then people started using it because you can flex it. But what happened is because of oxygenated water on the inside, they ran out. Polyethylene absolutely needs antioxidant package. You need to fill in the polyethylene very small molecules that will capture the oxidation of on the surface of the polyethylene. If you don't do the story I've been telling is it's going to turn like wine. It's going to turn vinegar. If you open a bottle of wine and you let it go, it's just not good. If you capture it, you control the reaction. It doesn't accelerate. If you don't have molecules to capture the product of oxidation of polyethylene, it will accelerate the oxidation process. So that's how you form the blister right here. You make the inside like cheese, look like cheese, and you corrode the aluminum layer, and when you get to the outside, it's just bursting out. So we can skip that. You can use the same type of approach with the plastics that we talked about for the metal in terms of fatigue. You can have a crack propagation analysis that's based on linear fracture mechanics. We have the Paris equation that's giving us a constant rate between the log of stress intensity and the crack propagation rate. These are some of my experiments. Here you can see in fatigue, the epoxy is really terrible because it doesn't form that plastic zone that we talked about. So it's just going to crack right through. And some of the very resistant alloy are nylon type. In total life, so this is when you don't have a notch, you see the opposite effect where the epoxy is doing well because it has a high yield strength. And it has probably a more decent resistance to crack initiation as well. Creep rupture, you can look at it. This is what turns to be In most plumbing, under pressure, like those gas pipeline, people have to look at the creep modulus after 50 years. That's what the design is based out of. And what I like for you on this plot is to see that if I run a 100-hour test, that's more than 4 days. So it's still significant effort on one sample. I get a value that then I have to divide by something like a factor of 4 to know what's going to happen after 50 years. So when you do the tensile test, the oral, you have no idea what it is. If you do a 100-hour, you start having some idea. So I hope today you got some idea about the effect of the environment. We talked about it for the aluminum. We talked about it for the plastic. We talked about molecular weight for all this stuff, all the plastics. It's very important if you want to prevent fracture. And there are many other things. The viscoelasticity is very important if you're looking at a polyethylene pipe. So just to put it very quickly for the plastic. So toughness is kind of okay, but it's dependent on molecular weight. This is not good for temperature application. It's good for corrosion, but it's sensitive to UV light. I haven't had the chance to talk about that much. It's sensitive to solvents. It can have terrible environmental cracking. It's okay for fatigue if the load is very low. It's okay for wear if load is very low, but it's not really its strength. Processing, making it to net shape, and cost in general is what makes those plastic good. Joining is possible. Solvent cement is one example, or the heated joint, but it's a lot more involved, and it's normally at reduced properties. So thank you for your attention. I'll have office hour tomorrow at 2 o'clock. That's in 4049.